I'm David,
And I'm Krisha.
and today we're going to be talking about the data collection and analysis for our calibration project. So this is the Excel sheet where we did all of the data collection and analysis. Um, it's split into three sheets here. The first one is just the raw data, where we entered our data as we performed the measurements in the lab. And then the second sheet is where the bulk of the work was performed. It has our raw data as well as all of our calculations and analysis to determine the behavior of the measurement device. The final page here is just a summary of all the calibration results. And this is just a quick place to find the overall behavior and calibration results here. So starting out with the raw data, we have the reference values on the left here. These are the values that were displayed by the DC power supply. So we called these a set reference, although there was some deviation in them, as can be seen in results. But for purposes of this lab, we called this our reference. These columns over here to the right are the measurements from the DC voltmeter. And so we're going to look at the first cycle here. We started out with a reference value of 0.01 volts, and we measured 0.008225. We repeated this process for each corresponding reference value as we went through our up cycles up to a peak value of 20 volts, and then we stepped down all the way to our starting value of 0.1, recording values at each step. This aligns with the ANSI standards for the calibration procedure. We repeated this procedure 10 times to ensure sufficient data was collected for the proper analysis of the measurement device. Moving over to our results and calculations page, we started out by just copying the raw data in here, make it a little easier to do our calculations from. Under here, we have our errors for each element. And so you can see the formula here. This is just the measured value minus the reference. And we did this for every cell in this table. We then took all of these values and found the average, which gives us our average error. And that was found to be negative 0.000547 volts. Coming back up here, we have the average for each cycle, and this is essentially just the average of all measurements for each reference value. I'm not sure what is happening here. Okay, so these are the averages for each corresponding reference value. And so this gives us an average measurement for each value there. Errors were determined by subtracting this average measurement from the reference value. And then our best fit values were determined using our linear regression. So the linear regression was determined by first plotting this calibration curve, which is the measurements versus the reference values. And then we used that plot to determine a trend line here and display the equation. And so this is our best fit model. We did do this with a little bit more resolution by using the slope function and the intercept function. And that gave us these values for y equals mx plus b. This slope is our m value, and this intercept is our b value. So coming up here, our best fit values, these are found by just plugging in our reference value into that equation. And we use this to determine our deviations. So the deviations were found by subtracting the average measurement, subtracting the best fit value from the average measurement. And you can see across the board here, our deviations were very small. In fact, our average deviation was 0 out to 6 decimal places. And pretty good results there. The next 4 columns are the upcycle averages. So the upcycle was found as we incremented up from 0.1 all the way to 20 volts. And then the down averages were as we counted down from 20 volts back down to 0.1. So we had to manipulate this a little bit since the averages here, they are pulled directly from this column. Sorry, this column. But we had to index them so that the reference of 0.01 corresponded to the same row for both the up and down averages. So this was performed using an index function that essentially just inverted those rows so they all lined up properly. The errors, again, same process here. They're just copied and pasted directly from this errors column, and these are inverted using the index function. Moving on here, and these are also our errors were also plotted against our reference values here. So these are our errors, and they're plotted against the references from the DC power supply. We also plotted the deviations that we just found against our references, and it gave us this scatter plot that gives a behavior, kind of an outline of the behavior for this measurement device. Moving on here to the accuracy limits for this device, we found this in 3 different terms. The first one is the absolute value in terms of volts. We then found the percent span, which gives a accuracy as a percentage of the total span, which our span was 0.1 to 20 volts. And then our accuracy from the deviation limits was found by taking the deviation, the maximum minimum deviation, and since our accuracy was not evenly distributed around the measured values, it gives a little better approximation there. So our calculations for that were shown here. This is essentially just the absolute value, the maximum absolute value of our errors here. So the largest error, we just make that a positive value and we get that there. The rest of these columns are just used to combine these values and strings so we get a nice readout like this that says accuracy limit, gives our units and everything there. The next column here is our percent span, and that just uses our absolute value, divides it by 20 to normalize it, and then multiplies it by 100 to get a percent. And then our deviation limits method, we just take the maximum of our deviation column and then the minimum of our deviation column, and we apply that. So our upper bound is this one and our lower bound is this one, as you can see here. And again, that gives a better approximation of the accuracy since it's not symmetrical around the measured point. The hysteresis errors, these were found by taking the absolute value of our up minus down averages. It doesn't matter which way you did them. It's essentially just the difference between the measurement in the up direction, in the up cycle, and the down cycle. So we did that for each of the reference points, and then we used a max function to find the max value of that, and that is the accepted hysteresis error for this device. The systematic error is simply the average of all our errors that we found for each reference value here. And that was found to be negative 0.00055 volts. And then we looked into the repeatability, which is concerned with if you were to repeat this process 100 times, how accurate are these results going to be over that entire range? So the repeatability range here, it was found by just subtracting the maximum of all our measurements from the minimum, or vice versa, the minimum from the maximum. And that gave us these range of values, essentially our deviation between our maximum and minimum measurements for each reference value. We then took that and divided the maximum of this repeatability column by 2, and that gave us our repeatability error in terms of volts. And then to determine that as a percentage of the span, we took that same maximum, divided it by 2, but then we divided it by the maximum minus the minimum of our reference values here. So the largest difference between the two reference values. And then we multiplied that by 100 to, which again, that just gives us our span. That's just 20 minus 0.01. So that normalizes it, and then we multiply it by 100 to get the percentage. So as you can see here, our repeatability error in both percentage and absolute value is very low. It's very strong results for this process. So that covers our analysis section, and then we'll just quickly show the summary of results here. Again, we have our best fit model, overall error, deviations, very good, accuracy. You can see all these here. So that concludes the data collection and analysis portion of the calibration project. Thank you for watching.